Start case number 12. We will first insert these parts, and so I'll do constrain and I'll select insert. I'll select this circle and I'll select this circle back there. Of course I want this on the other side, so I'll flip that around, and then I'm going to do mate. So I'll select mate, I'll select this axis, and I'll select the axis of this hole, and I'll say OK to that. So now if I move this part, it translates. If I move this part, it rotates. Now this part will actually rotate, so it rotates and translates. We'll want to take care of that in a few minutes. But if I go to dynamic simulation, and I see that I had already left some stuff in here from a previous run that I didn't really intend to have in there, but anyways, so right now I have a cylindrical constraint which I want to change that to prismatic, and then I have a revolution joint up here. So we'll go back to dynamic simulation. I'll save my file, and the assembly environment, and then I'm going to try to do a tangent constraint between this face and this face, which it does put in that tangent. But now notice as I rotate this around, when it gets to this line, it doesn't follow that face. So we can't use a tangent because a tangent is only between two faces. You know, this being one face, and so this is 1, 2, 3, 4. So we can't do tangent. So that was one of the questions: is why can't we do tangent? Tangent can only be between two faces, not multiple faces. And so I'll delete that tangent, and instead of tangent I'm going to use a transitional constraint. Now I'm never sure which one I need to pick first, the moving face or the transitional face. I'm going to guess, and if I get it wrong I'll just do it the other way. And so I'm going to guess this is the face I need to select first and the face I need to select second. And I see that when I move this now, it does move the valve. But this constraint, the transitional constraint, does not get converted to a dynamic simulation joint. So if I go to dynamic simulation, we still see our cylindrical and our revolution joint. So what I want to do is put a 2D contact between this and this part. And so I need to get something I can use as 2D in this valve. So I'm going to open up the valve, and I will edit sketch 1, and I can see that there is a 3mm radius arc here in sketch 1. Let's go ahead and finish sketch 1, but we'll make that visible. And I'll start a new sketch on that same plane, and I'll project geometry this arc from sketch number 1, and then I'll turn off the visibility of sketch number 1. Alright, so I have that arc. You might hit F7 for slice graphics so that you can see inside of the part. And I'm going to change that to construction so that I don't accidentally select it later on. And then I'll draw a circle from here over to here. We see that that circle is fully constrained. Now I'm going to go ahead and extrude that circle, and so I'll do extrude, and I'm going to do that though as a surface body because I don't want to add any mass to this part. And so I'll change it to a surface body. I'm going to extrude that mid-plane 10mm. And I'm going to go leave that sketch visible though, although I don't really need it. But I'll leave that sketch visible. Alright, I'll go back to the assembly. Now we can see now that this part still rotates, and in order to do a 2D contact joint we can't have this part rotating, so we need to put an appropriate constraint on there to keep it from rotating. So in the real world now this part can rotate, but we only want it to translate. In fact, in the real world, when this part rotates a little bit, it starts to wallow out, or it pushes against this edge right around here, and that edge gets bigger and bigger, and there's a seal that goes over there, a rubber seal, and as that edge though gets bigger, oil leaks down past the valve, and then that little bit of oil sits here on the edge of the valve. We're talking about just a tiny film of oil, And then when you start up your car in the morning when it's cold, you'll get a big cloud of white smoke when that oil burns coming out your tailpipe. And it'll only last for a minute or so, a couple minutes, until it burns off all that oil that leaked past the valve stem. And so that's when you need to get a valve job to replace the valve seals, and they'll probably go ahead and do some work on they knurl the holes actually to displace the metal to make the holes smaller. All right, let's see. So we need to find that appropriate constraint to line that up. So I'll go to the valve, and I could use either the XZ or the XY. I'll constrain the XY flush, and we'll hope that in this the XY plane is also where this part is, or the support. We can do that either at the assembly or here. And so when I do that, now this part no longer rotates, it only translates, and it'll move so it'll only go up and down. It doesn't rotate anymore. And when I go back to dynamic simulation, we'll see that is now a prismatic joint. It's not a cylindrical joint anymore. So a lot of people miss that step. It's important to do that step. Now, when we come to dynamic simulation, though, we see that translational constraint isn't converted to a dynamic simulation joint. So I want to do a 2D contact, and I can either use the edge of this surface, or I can use the circle back here. And hopefully I can use the face of this and use the edge of it. Now, in earlier releases of Inventor, we sometimes had to project this face to a 2D sketch in order to get it to work. But let's see if it'll work. So I'm going to do a 2D contact. And again, I can either select this circle or the circle back here. Now, if I get back here, I want to make sure I get that circle and not this construction arc. So I'll get that circle. And then I'm going to select this face, and it looks like it's going to accept it even though it doesn't highlight it all the way around. So Z should be pointing to the outside of the cam and to the outside of the circle. Sometimes you'll need to flip the Z on the circle. Now, if this doesn't work for you, you will have to project this edge onto a sketch so that you have a sketch just like this circle sketch. And let's see, so it says FEA is not supported for contact forces. We'll take care of that later on. Alright, so now if I move this part, we see that it does come in contact and move that, but I need to put a spring force on here holding that up against that 2D contact. I'm going to set this revolution joint though first where it is at 0, either 0 or 180. So I'll go to the revolution joint, and I'll go to the properties at 1 degree of freedom, and I'm going to set this at 0 degrees so it's straight up and down. Now, depending on how you put this together, it might actually be 180 degrees, but I want it straight up. And this is the maximum opening on the valve is when it's against this circular face of the cam. And I also want to change that. I might edit that the 2D contact properties, and I forget whether I said to put a restitution value or friction value in here. I'm going to put that restitution at 0. And I think for now I'll leave that friction where it is. Now I want to drag this down, and I want to drag it back up and make sure that it's tight against that cam. All right, and then I'm going to go to my spring force, and so I will go to the properties of that spring force, and we see that the free length is set to 50 millimeters. Now I intended for you to actually put that in yourself, so I don't remember if that is what it is right now or if that is the number that I put in. So let's go ahead and measure this. So I'll go back and I'll go to inspection tab, and I'll measure this distance from here up to here, and I see that's 49 millimeters. So if I set the free length at 50 millimeters, then I have already a 1 millimeter preload. We've compressed that spring by 1 millimeter to start with, and then we have 100, so 100 newtons per millimeter, so there's 100 newtons of force holding that up against there. In the real world, if you ever do a valve job on a car and you go to take the springs off of the valves, there'll actually be an outer spring and an inner spring, and you have to use a special tool in order to be able to remove those springs, because they're incredibly strong springs. They're really stiff springs. So when you see information about what percentage of energy from a gallon of gasoline actually makes it to the axle, one of the losses is in compressing these springs. It takes a tremendous amount of force to keep that spring, or keep this valve against the cam. So as you go faster and faster, when you approach 7,000 RPMs, the valve wants to float instead of returning back up against or keeping against the cam. It'll try to float in space, open when it's open. And if the piston comes up and that valve is floating, it will hit the top of the piston and either bend the valve or put a hole in the top of the piston. In any case, your engine is going to stop working. So it takes two incredibly strong springs in order to keep that valve against that cam face when you get over a certain number of RPMs. Okay, I want to rotate this cam. So I'm going to go to the revolution joint, and I'll go to the properties, and 1 degree of freedom, and I'm going to do a constant velocity, 360 degrees per second. Now we're just turn this real slower than it would be in the engine, but all we want to do is get the curve. And so 360 degrees per second. I'm going to run this for 1 second. I'll do 100 calculations, and let me go ahead and display the output grapher. And I want to keep track of the acceleration of this valve. So I'll go to the prismatic and I'll turn on the acceleration curve, and I'll go ahead and play this. Now this went counterclockwise. I wanted to go clockwise, but for our cam the curve will be the same. So let's rewind this. I want to make a screen capture of some of this information. So I want to change the direction of this rotation so that it is rotating clockwise. So I'll go to the revolution joint and I'll do edit, and I'll flip the Z-axis, and I'll say OK to that, and we will play it again. 1 revolution. Now it's going clockwise. All right, I want to keep a record of this curve, so I'm going to save that curve, and I'm going to call this original cam valve, and then we'll create a new cam and compare the acceleration curve of the new cam to this original cam.